Hello students, in today's lecture we are going to learn about electric charges and fields, and this is theory part 6. In today's lecture our main focus to learn how to calculate electric field from two important charges distribution. First is an infinitely long straight wire with uniform charge. Second is an infinite plane sheet with uniform surface charge. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So, imagine a very long, uniformly charged wire. So, suppose we have a very long means infinite. Look at figure B. So, we have a infinitely long charged wire, so long that its end don't matter. So this is infinitely long. So let the linear charge density of this infinitely long straight wire is lambda. So the case describes an infinitely long thin straight wire with uniform linear charge density lambda. So what will be the value of lambda? Charge per unit length. So it will be what? Charge per unit length means charge divided by L. L is the length. It means lambda will be Q divided by L. Due to symmetry around the wire, suppose we have a wire, this one, infinitely long straight wire, and due to symmetry, P prime and P double prime. Look at here. P prime and P double prime obtained by rotating like this, in this manner. Rotating a radial vector have equivalent electric field magnitudes. So the radial vector is R. So when we rotate this radial vector along a in, we can say, in anti-clockwise, so it form like a circular. So the electric field at every point, at point P, at point P prime, at P double prime are same because the distance is same. And the direction is what? The direction of electric field is radially outward. This is very important. Radially outward for positive charge and inward for negative charge. How we can know about the positive charge and negative charge? So if the linear charge density, that is lambda, is positive, linear charge density is positive, so we can say the direction is radially outward. And if the linear charge density lambda is negative, so it means the direction of electric field is radially inward. Clear? Here we know lambda is equal to what? Charge upon length. Lambda is equal to charge is what? Q divided by L. Clear? For line element P1 and P2, P1 and P2. Look at here. P1 and P2. Their combined electric field gives a radial resultant as normal components cancel. This applies to all such pairs, making the total field radial at any point P. So initially we consider a small length element at point P1. The infinite wire means field depends only on the radial distance. It means what? It means if we talk about the at point P, and if we talk about the at point P prime, the electric field at every point is same because the radial component is same. Now if we talk about the another radial component, suppose that is R prime, in that case electric field is vary because R prime is greater than R. It means the electric field depends upon the radial component. It not depends upon the length of the straight wire. This is the particular case of the wire. Here the electric field does not depend on the length of the wire. Here it depends only on the radial component. So this infinite wire means field depends on radial component R, not position along the wire length. It does not depend on length of the wire. So here we consider this is the infinitely long wire, and we consider a small length element, this one. Now due to this small length element, we will find out the electric field at point P. The distance of wire and point P is R. Clear? Distance is R. Now as we know, when we draw or when we move this point P along P prime, P double prime, the electric field is same. So it means it depends on radial part. So for calculating the field, now we will calculate the field at point P. Consider a cylindrical Gaussian surface. The Gaussian surface we can assume like this. So this is a cylindrical Gaussian surface. This one, the dotted region. The radial field means zero flux through cylinder ends. At the cylinder surface, E is normal with constant magnitude. So if we want to calculate the direction of electric field, the direction of electric field depends on here the charge. Here charge is positive, so it is perpendicular to the surface, or we can say line element. So surface area of the curved part is what? It is 2 pi RL, where L is the length of the cylinder. Our main aim in this topic is to calculate electric field at point P due to infinitely long straight uniformly charged wire. This wire is charged. Clear? So the flux through Gaussian surface equals flux through curved cylindrical part. So it will be what? E into 2 pi RL. So this is the flux. For charge lambda L enclosed, we know what is Gauss law. The total flux through is equal to total charge enclosed by the closed surface divided by epsilon naught. This is the Gauss law. And what about the linear charge density? So it will be density lambda. Here we talk about the linear. So it will be lambda is equal to charge upon length. So charge become what? Q equal to lambda L. Q become lambda L. So this is the charge and this is the flux. Q enclosed divided by epsilon naught. So from Gauss law, it gives E into 2 pi RL, which is equal to lambda L divided by epsilon naught. Lambda L is what? Lambda L is charge. So from this relation, what is the electric field? Therefore, the electric field is equal to lambda divided by 2 pi epsilon naught R. We know this from Gauss law. Phi is equal to Q enclosed divided by epsilon naught, and lambda is equal to charge divided by length. So it become charge is equal to lambda L. Yes or no? Or just substitute the value of charge in this relation. So you will be get the value of flux. Now value of flux is what? Q into E into A. So just substitute, you will be get E. E is equal to become lambda divided by 2 pi epsilon naught. I hope this is clear. So vectorially E equal to lambda divided by 2 pi epsilon naught n cap. What is n cap? N cap is the direction which is perpendicular, where n cap is a radial unit vector normal to the wire. So here n cap is the direction like this. N cap shows the direction which is the normal to the wire. For vector notation, it will be A equal to A vector. Area vector is equal to A into A cap, where A is the magnitude of the area vector and A cap is the unit vector. A is algebraic. It should be any positive number and negative. And direction follows A cap. If A is greater than 0, if the magnitude of A is greater than 0, so and opposite, so it will be opposite. And if A is less than 0, so modulus of A is non-negative. Through calculation uses enclosed charge, that is lambda L. Now we know linear charge density is equal to charge divided by length. So it will be charge is lambda L, and field E results from entire wire's charge. So infinite wire assumption ensure E normal to cylindrical surface. E normal to cylindrical surface. So equation approximately holds for central portion of long finite wires. So ignoring the effects. So the equation holds only for a central portion, not for ends upper and lower, because this is infinitely long straight wire. Due to this infinitely long straight wire, the electric field due to endpoints is negligible. Look at here. This is charged infinite plane sheet. This one, charge infinite plane sheet. Now we will calculate the electric field due to this uniformly charged infinite plane sheet. So the figure, Gaussian surface for a uniformly charged infinite plane sheet. The given configuration has uniform surface charge density sigma. If we talk about the continuous charge distribution, what will be the linear charge density? It will be charge divided by length. And if we talk about the surface charge density, it will be the charge divided by surface area, and where surface charge density is sigma. So the surface charge density on a infinite plane sheet. This is infinite plane sheet with x-axis normal to the plane. And due to symmetry, the electric field depends on only x-axis. So the direction of electric field is here. If we talk about the right phase, so it will be perpendicular to the sheet. It means like this. And if we talk about the left phase, it will be like this. Direction of electric field. It means electric field is perpendicular to the plane sheet. We can say infinite plane sheet. The Gaussian surface chosen is a rectangular parallel pipe with cross sectional area A. So to find out the electric field, first of all we choose the Gaussian surface. So here the Gaussian surface is this one. This dotted line is this one is the Gaussian surface. So area of cross section covered is only this one. Only this one. This is area of cross section. Now we will find the electric field due to this uniformly plane charge sheet. So the cross sectional area is A. Only phase 1 and phase 2 contributes the flux, since the electric field lines are parallel to other phases. So the distance is from the center. If we talk about the right phase, so it will be x, and from left phase it is also x. So surface first, this is surface first and this is surface second. Surface first has a unit vector in x direction. In x direction, it means the area vector is perpendicular to the surface and the direction of electric field is along x-axis. If we talk about the second surface, so here area vector and electric field both are parallel, while surface 2 has in its x direction. So the flux E dot delta S through both surfaces are equal and additive, giving a net flux 2EA. So the net flux due to phase first and phase second is 2EA. Now this is the flux. Now we will calculate the electric field. And enclosed charge is sigma A due to surface charge density. So here we are applying the Gauss law. So what is Gauss law? So total flux is equal to total charge enclosed by the closed surface divided by epsilon naught, or we can say total flux passing through a closed surface is equal to total charge enclosed by the closed surface divided by epsilon naught. So here the total flux is what? This one, phi equal to 2EA, and total charge is this one. How this comes? We know flux phi is equal to E dot A. E dot A, yes or no? E dot A. So it will be E A cos theta. Now if we talk about the phase first. So here the direction of electric field and direction of area vector both are parallel, because both are perpendicular to the this plane. So theta will be what? Theta is equal to 0 degree. Yes or no? So cos 0 is equal to what? 1. So flux through phase second is what? It will be EA. Clear? Now what about the flux through phase first? It will be also EA. Why? Because the direction of electric field is and direction of area vector both are parallel. So theta is what? Theta is equal to 0 degree. So again here theta is equal to 0 degree. So flux through phase first is this EA. So net flux is phi 1 plus phi 2. So it will be what? 2EA. Clear? So this is the net flux. Now what about the charge? So here the charge is we will calculate using the surface charge density. So surface charge density is sigma is equal to charge upon area. Charge upon area. So here charge is what? Charge is equal to sigma into area. Now substitute the value of charge sigma into area divided by epsilon naught. Yes or no? So it will become this equation. So solving this you will be get E is equal to area cancel out. So E is equal to sigma divided by epsilon naught. So it is the electric field due to a uniformly charged infinite plane sheet. Electric field due to uniformly charged infinite plane sheet. Clear? So vectorially electric field is equal to sigma divided by 2 epsilon naught n cap, where this is the magnitude sigma divided by epsilon naught and n cap is the direction. Now what is the electric field due to uniformly charged infinite plane sheet? That is sigma divided by 2 epsilon naught. Clear? Here n cap is unit vector normal to plane pointing outward, and field E points away from the plate of positive sigma and toward it for negative sigma. Important point is here E is independent of x. Here E is independent of x. This is very important. So for finite large planar sheet, this results approximately holds in middle regions away from edges. Thank you for your attention.